So here you see an example that's the same example like here. You have different attributes that are relevant for different clusters. So this is a three-dimensional data set. Here is the data set. It's probably a big cloud of points, and there is no, in the three-dimensional case, I mean, forget about the color coding. There are 4 clusters, color-coded of course, but if you forget about the color coding, this is just one big data set which is not extremely clearly structured in the three-dimensional case. And if you project that on what is that? That is probably the y-x-axis. Then you see that those 4 classes are completely overlapping. Yeah, you have a clear structure if you know the color coding, but still consider you don't have the color coding here. It's just one big soup. A little regularly, okay, but in the end it's one big soup. So density-based clustering wouldn't make sense at all. K-means would come up with probably 4, especially if you know that it's 4 clusters, will come up with 4 spherical things here in the corners of the data set. Yeah, but now if you look at the correct two-dimensional or different and the right different right two-dimensional projections. So this one here is obviously this projection here, the z axis projection. Then you see that you can find the red and the green cluster. At least you can distinguish those 2 clusters from the other 2 clusters which are not separable here. Yeah, and if you have a look at the what is that ZY axis, is this one here, then you see that you will find the purple and the blue cluster, and you will not have a chance to distinguish this one here. Yeah, so looking at different subspaces gives you different clusters, different patterns. And again, the red and the green one can only be detected in a different subspace than the subspace that has to be considered to detect the purple and the blue one. Yeah? So different subsets of attributes, subsets of features, projections are relevant for different clusters. Yeah? Here is a different one than here. Yeah, and it can even be a little bit more complex, because typically in reality the data doesn't look exactly like this one here, but things are correlated. Yeah, so in that case it's not axis parallel like here, but it's somehow transformed, not flipped, but somehow transformed. Yeah, and then you end up in something like this one here. So again, some real world motivation. The task is cluster test persons to find groups of individuals, patients typically, with similar correlation among concentrations of metabolites, and that indicates some metabolic behavior, for example, some disease. Yeah, so this is the case of the Bavarian newborn screening. We worked on that data actually, and the task was, well, I think you probably remember. So they take the blood of each newborn in Bavaria, and then they measure concentrations of metabolites, something like 50 or 60. So it's a 50 to 60 dimensional feature space, and now you want to cluster the babies, yeah, and you want to find groups, and the groups, the different groups are consistent according to concentrations of metabolites, or at least subsets of metabolites. Yeah, and those correlations indicate especially disorders. Yeah, so something like this one here. So here is a kind of positive correlation. So it's obviously an idealized figure of only a two-dimensional case, but now consider that to be 50 dimensions. So you have one disorder, which is a positive correlation here, and another one is a negative correlation, and then you have a big cloud of healthy people, of healthy babies here, which is in that case no correlation at all. Yeah. So what you see again here is that different metabolic disorders appear through different correlations. Yeah, so this one is a negative correlation, this one is a positive correlation, two different correlations, and that is more or less the same picture as we had before, but now, as I told you before, not axis parallel anymore, but the whole thing is just, you know, somehow transposed or transferred into an non-axis parallel subspace. Yeah, now a subset of features may be correlated, groups of similar points may be identified when considering this correlation of features only. Yeah, so in this case we can see that if we project those guys here onto this red subspace here, those guys are extremely similar in this new feature. Yeah, and in the original features and also in this one here, of course, they are not. Yeah, so it's the same picture as before, like here, but just it's not axis parallel anymore, but we are now talking about correlations. Yeah, and again, different correlations of attributes may be relevant for different clusters, like here. Yeah, so we have different correlations for the different clusters. Okay, so this sounds or looks a little bit familiar to you, right? I mean, what did we do last week? We tried to find those correlated directions, the directions of high variance, which is actually exactly the black one here, the black dashed one direction here. So if we find this one here, we just have to project them on the orthogonal feature space. So on the if we apply PCA here, we get this direction and this direction, and now we just take not this direction as before, but we just take the other direction of the features we usually discard when we do feature selection. Sorry, with PCA. Yeah, but unfortunately, that's too easy and too short. So yeah, why not? Why is that too easy? Well, feature selection, unsupervised feature selection like PCA, is global. That means it transforms the original feature space into one new representation, only one. Yeah. However, we need several of them because we need this one here and this one here and this one here. Yeah, we face a local feature relevance, local in terms of local for a given cluster. Yeah, so some features may be relevant for one cluster locally, but they may be completely irrelevant for a second one, because for the second one we need another local feature correlation. Yeah, so we probably need multiple local feature representations or feature correlations, feature relevances, in order to detect all of the patterns we want to detect. You know? And that is the big problem here, why feature selection, global feature selection like PCA or SVD cannot do the job, because they just can find one big feature space. And we will have a look at on this example actually how PCA would perform. So let's perform PCA on this data set. It's the same like here. Yeah. So let's perform PCA on this data set. Okay, we will get the first principal axis and probably the second principal axis. And now, since we want to do dimensionality reduction, I mean, maybe somebody told us that we are looking for those correlations here, so we need the direction of the correlation. Yeah, so we take PCA, project everything on the first axis, the same with the second axis, by the way, but we project them on the first axis, like this one here. You see, we end up in a big soup where nothing can be seen anymore. Yeah, so for example, if we apply dbScan on that, we end up in one big soup, depending of course on min, PTS and epsilon, the parameters. Everything is in one cluster or everything is noise. Yeah, and obviously this does not give you the desired result. Why? Because we with PCA we only get one global correlation or feature relevance, but we need for each cluster we need different ones, local ones, and PCA is a global approach. So you may think that, well, just doing it the other way around, cluster it first and then apply PCA in order to see or to find out the correlations of all the different clusters. Well, let's do that. So apply dbScan on this one here. Well, it will find, depending again on the parameters, but the whole thing here, the red dots here, is that the density among all the red dots here is quite consistent, yeah, all over. I mean, maybe here and maybe here there's a break, but not really, yeah. So we will miss a lot of things here, but at least those guys here is one big cluster. Yeah, we may be lucky to find the noise points here, but the rest will be more or less arbitrarily one big cluster. Yeah, so if we apply PCA on this found cluster, we again end up in something which is not what we want. Yeah, so we have the problem again that of course dbScan is not designed to look for those local correlations. It is designed to find dense areas, and well, if this is not 2-dimensional but 100-dimensional or 50-dimensional, dbScan will probably also mix everything up. Yeah, so even the noise points may be mixed up in the clusters or in the big cluster. So summing up, we have feature relevance and correlation. Yeah, so no clusters are usually can usually be found in the full dimensional space. Often clusters are hidden in subspaces of the data, so only a subset of features is relevant for the clustering. Yeah. So the example is a group of genes may play a common role in a subset of experimental conditions, but they may behave completely different in other conditions. Yeah? So the conditions are the features, the genes are the objects. So depending on which experimental conditions I consider for the clustering, the features, we may have completely different groups of our objects. And the features relevance and the feature correlation is local or maybe local. That means for each cluster, a different subset of features or a different correlations of features may be relevant, like this one here. Yeah. So local feature relevance, local feature correlation. So again, the explanation for that, or the example for that, is that different genes are responsible for different phenotypes. And yeah, that's it. Other conditions is a copy paste from up there. Sorry for that. Yeah, and to make the things even worse, so we not only have local feature things, but we may have overlapping clusters. We are back in the baby shape game, so we may have different semantic concepts. That means one object may be in different clusters depending on which projection, which local feature relevance, which local feature correlation I consider. Yeah, so clusters may overlap. An object may be clustered differently in different subspaces. For example, a gene plays different functional roles depending on their environment of the conditions. Yeah, the other conditions, I have a copy-paste problem, I think, here on this slide. But anyway, yeah, I think you got the point. We have feature relevance and correlation that is local. And we may have the problem that we have even overlapping clusters, so really different semantic concepts. Objects may be in completely different and more than one cluster in completely different clusters depending on which local correlation, which local feature relevance I consider.